Right, in the last video about cycloalkane isomers for Chem 230 online, we looked at an introduction to some of the terminology that we're going to see. So cis means two substituents are on the same side of the ring. Trans means two substituents are on opposite sides of the ring. And that's what it says here on this slide, cis or trans. And those are the words you would use to distinguish different geometric isomers. Where things are connected in the same way, they're just facing in opposite directions. So you have a methyl on carbon number 1 and a methyl on carbon number 2, but one can be facing up, the other could be facing down. That's going to be sort of the geometry of which way things are facing. So that's something that's important. And what will be useful here, I think, is to go through a couple of cyclohexane examples to show distinctly the difference between constitutional isomers, geometric isomers, and conformational isomers, or conformers. So let's slap into it. The constitutional isomers means things will be connected in different ways, or the substituents will be connected on different carbons. So if I draw a cyclohexane ring and I put, and we'll do some chlorines this time, a little different. If I put a chlorine on the first carbon and then a chlorine on the third carbon, this would be 1,3 dichlorocyclohexane. So 6 carbons in a ring with 2 chlorines substituting for the hydrogens. And the thing I'm focused on here is the constitutional part, is which atoms are the chlorines connected to. You could do another cyclohexane, and like we did with the dimethyl example in the last video, you can put a chlorine or a methyl or whatever on the first carbon and then another one on the second carbon, and this would be a 1,2 dichlorocyclohexane. And so depending on where the substituents are connected, they're different constitutional isomers, and they're designated using the numbering system of how things are connected up. The other one that you'll see occasionally is when things are on opposite sides of the ring. So if you have a chlorine here and a chlorine over here, right, these guys will be 1, 2, 3, 4. If this is carbon number 1, this is carbon number 4. So you can have a 1,4 dichlorocyclohexane. So as we look at it, if you break it down individually, 6 carbons, single bonds, in a ring with 2 chlorines, one on the first carbon, one on the fourth carbon. So 1,2, 1,3, or 1,4 substitutions, fairly common. Now, one of the things that we mentioned last time is when we talk about the geometric isomers, things can either be cis or trans. So like this one, I've got the 2 chlorines both down. So this guy is going to be cis because both chlorines are facing down, they're both on the bottom of the ring. So this is where the constitutional isomerism is embedded in the numbering system. The geometric isomerism is in the cis versus trans language. And so with this one, the dichlorocyclohexane, this one's on top of the ring, that's on the bottom of the ring, so this would be trans. Trans 1,2 dichlorocyclohexane. And then this guy got 1 chlorine up, 1 chlorine up, so these both are up, so this would be cis meaning they're both on the same side of the ring. So whether something is cis or trans, you look at which side of the ring are the substituents on, and if they're both on the same side, it's cis. If they're on opposite sides, it's trans. And this is really, again, useful to see the models, because if you have a model like this, you could see pretty clearly that this model is the trans 1,2. You have chlorines on adjacent carbons, so if this is number 1, that's number 2. This guy is pointed above the ring, so up here, this one's below the ring. So if you look at the plane of the ring, tilt it a little so you can see the plane of the ring more clearly. This is below the ring, this one's above the ring. So there you go, trans 1,2-dichlorocyclohexane. And when you do the conformational changes, trans has to stay trans, and 1,2 has to stay 1,2. So as I go to make the conformational isomer of the same molecule, after it does some rotation and manipulations, what happens is any axial positions turn into equatorial positions, and any equatorial positions turn into axial positions. But if it was trans before, it has to stay trans now. If it was 1,2 substitution pattern before, it'll stay 1,2 substitution pattern now. So this guy had adjacent carbons with things in axial positions. When we do the conformational change, you're going to have the 2 chlorines go to equatorial positions, but they're going to stay trans. So if this guy is below the ring, right, he's in an equatorial position, the axial position moves to an equatorial position, then the other axial position moves to an equatorial position. Now this chlorine is below the ring, this one's above the ring, so it's still trans. So this is trans 1,2-dichlorocyclohexane as well, but it's changed its conformation, so now the chlorines are in equatorial positions where they were in axial positions. And that means with both of the big groups in equatorial positions, this is a low energy conformer. And with 2 chlorines in axial positions, this is the high energy conformer, right? And so if I wanted to do conformational change for this molecule, the one at the bottom, the cis 1,4-dichlorocyclohexane, the axial position turns into an equatorial chlorine. The equatorial chlorine turns into an axial chlorine. It stays cis before they were both on top of the ring. And actually, as this goes, they would still both be on top of the ring if I actually did the transformation properly rather than just redrawing it. So I essentially drew this upside down, but the equatorial position turns axial, the axial position turns in equatorial. So these 2 conformers are the same thing in the same energy. They can undergo a conformational change that results in something of the same energy. So this is still cis 1,4-dichlorocyclohexane with one position axial and the other position equatorial. If we had the models, then we could do the manipulation of the model to show the change from axial to equatorial position and how these guys stay on top of the ring. They just change their relative positions. This is drawing the same molecule but in different form. The molecules I have, which are really cool, they're very sticky in how things are connected. So if I try to take this trans 1,2-dichlorocyclohexane and then manipulate it, going a chair to boat to chair configuration, it ends up being a lot of work and sort of difficult to get everything to get back into a chair conformation like it's supposed to be, because things stay a little sticky. But there we go, I sort of had moderate success there. I've got it back in a chair conformation, same molecule, didn't break any bonds, and now you can see that above the ring and below the ring chlorines are both in equatorial positions rather than axial positions like they just were. So you can rewind the video a little bit, show that this molecule was diaxial, was this guy. I twisted things up a little, not breaking any bonds, and I got it in this form. So axial positions can turn into equatorials, equatorials can turn into axials without breaking bonds. And so this one, which is the cis-1,3 dichlorocyclohexane, right? If I do the conformational change, it's still going to be cis-1,3 dichlorocyclohexane, but what happens is the axial positions turn equatorial and the equatorial positions turn axial. So the equatorial positions turn axial, then 1,3 substitution pattern, this will still be cis because they're both on the same side of the ring, but now it's going to be higher energy because they went from being equatorial positions to being axial positions. Both of them, they went from the low energy conformer to the high energy conformer, and this is going to require heat from the room to do this, to move to a higher energy conformer, but it's certainly possible. Alright, so there it is, the constitutional isomerism in this system, disubstituted cyclohexanes, is designated by the numbering system. The geometric isomerism is notated by the language cis versus trans, and then if you have one molecule in a particular chair conformation, if you undergo a conformational change via the chair-boat-chair interconversion, it's called, you can just put, for an introductory course, some magic happens to turn equatorial positions into axial positions. It retains its constitutional and geometric isomerism, or if it was cis-1,3, it stays cis-1,3 dichlorocyclohexane, but now the equatorial positions turn into axial positions and vice versa. So a little complicated, but if you work through each of the types of isomerization, how things are connected is constitutional, which directions things are pointed, top or bottom of the ring, is geometric, and then whether they're axial or equatorial can be changed using conformational changes, then I think you can pretty much work through this. I'm going to come up with a sample question and post a video on that as well, so that you can get the hang of this.